Good morning, Doctor. We are from Electrical Principles 2, BNR 10303, Section 1, Group 6. Today we are going to present about our group project, and our lecturer is Dr. Noor Kamalia binti Abdul Hamid. Our group members consist of me, Mackenzie, Kirk Ming Teng, and Tan Po Zeng. Now I will pass it to my teammate Kirk to explain about the introduction.
Thank you. Now I will discuss about the introduction. So we have designed the three-phase AC circuits that use the concepts such as phases, impedance, RMS value, power factors, and complex power. We have chosen the simple three-phase AC circuits to simulate the factories of residence power distribution. The circuits consist of 3 resistors, 1k ohms, 3 capacitor 10 microfarad, and 3 inductor 100 millihenry. And we have used LED light to enhance visualizations. The circuit is powered by 240 volts and 50 Hz three-phase AC power supply. This project let us learn how to design the three-phase circuits and the calculation.
Thank you, Kumingding. Now I present of objective. There are 5 main objectives of this project. For the first objective is to construct a three-phase circuit with the utilization of voltage source, inductor, resistor, capacitor, and also for the LED. For the second is to perform the calculations of phases, impedance, power factor, RMS values, and complex power, and stimulate the same circuit using online circuit simulation software. For the third is to perform analysis on theoretical calculations with simulation and discover the key difference between them to further understand about the circuit analysis. For the fourth is to improve our communication skills and teamwork by demonstrating the ability to present technical information clearly, concisely through oral presentation and written reports. For the last is to collaborate effectively in a team to distribute tasks, meet deadlines, and integrate individual contribution into a cohesive project.
Okay, thank you, Tan. Now I will explain about the calculation part. As you can see, this is our circuit design. It is a three-phase system, and each phase differs from each other by 120 degrees. Due to the values of component in three phase are almost the same, we will be doing the calculation for the first phase only. Now we know that the voltage source has 240 volt and the omega is 100 pi radian per second. Now we will find the impedance in the capacitor, which is equal to negative J 318.31 ohm, and the impedance of the inductor is equal to J 31.42 ohm. Now we will find the impedance of the first phase. We know that the resistor is series with the inductor and they are parallel to the capacitor. So we will use the formula of parallel, and the total impedance for the first phase is equal to 306.12 ohm with phase angle of negative 70.2.19 degree. So now we need to find the current that flow through the first phase, and the formula is V1 over Z1, and the value is 0.784 ampere with phase angle of 72.19 degree. So now we will find the power at R1 resistor. We know that R1 has resistance of 1k ohm. By using the current divider rule, we will find the current that flow to R1 is equal to 0.2399 ampere with phase angle of negative 1.8 degree. Now we need to find the IRMS, which is equal to I peak divided by SERT2, and the value is 0.1696 ampere with phase angle of negative 1.8 degree. Now we need to find the VRMS, which is equal to IRMS times resistance, which is equal to 169.6 volt with phase angle of negative 1.8 degree, and the peak voltage is equal to VRMS times SERT2, which is equal to 239.9 volt with phase angle of negative 1.8 degree. The real power P is equal to the complex power S. This is because resistor does not have imaginary part. So the real power P and the complex power S is equal to 28.76 watt, and the value is absorbed by the resistor, and it has an apparent power of 0. Now we will look at the power and inductor L1. We know that L1 has a value of 0.1 Henry. We will find the IRMS value, which is equal to IRMS at resistance 1, which is equal to 0.1696 ampere with phase angle of negative 1.8 degree. and the I peak is equal to IRMS times SERT2, which is equal to 0.2399 ampere with phase angle of negative 1.8 degree. The VRMS value is equal to IRMS value times the impedance value of the inductor, which is equal to 5.329 volt with phase angle of 88.2 degree. The V peak is equal to VRMS times SERT2, which is equal to 7.536 volt with phase angle of 88.2 degree. The real power P is equal to 0 and the apparent power Q is equal to 0.904 voltage ampere reactive. The complex power S is equal to J 0.904 watt. Now we will look at the power at capacitor C1. We know that the capacitor has 10 microfarad, and by using current divider rule, we will find the current that flow through capacitor C1 is equal to 0.754 ampere with phase angle of 90 degree. The IRMS value is equal to I peak divided by SERT2, which is equal to 0.533 ampere with phase angle of 90 degree. The VRMS value is equal to IRMS value times the impedance value of the capacitor, and the answer is 169.66 volt with phase angle of 0 degree. The voltage peak is equal to VRMS times SERT2, which is equal to 239.94 volt with phase angle of 0 degree. The real power P is equal to 0. The apparent power Q is equal to negative 90.43 voltage ampere reactive, and the complex power S is equal to negative J 90.43 watt. Now we will look at the power at voltage source V1. We will find out that the real power at voltage source is equal to 28.78 watt, which is supplied by the voltage source. The apparent power Q is equal to negative 89.57 voltage ampere reactive, and the complex power is equal to 28.78 minus J 89.57 watt. So now we will look at the power at LED 1. We know that the current that flow through LED 1 is equal to 0.788 ampere with phase angle of 72.19 degree, and the voltage is equal to 2.238 volt with phase angle of 0 degree. So now the real power P is equal to 0.2697 watt, which is absorbed by the LED. The apparent power Q is equal to negative 0.840 voltage ampere reactive, and the complex power S is equal to 0.2697 minus J 0.840 watt. Now we will look at the simulation part of the circuit diagram to prove that the value obtained from the simulation is almost same as the value obtained through calculation. Now we will look at the simulation part. First up, we will measure the capacitor voltage V peak. As you can see, it shows that the max voltage is equal to 237.9 volt, and the max ampere is equal to 736 milliampere. Now we will look at the power consumed. As you can see, the average power by the capacitor is equal to 22.144 milliwatt, which is almost equal to 0. Now we will look at the resistor voltage peak. As you can see, the resistor peak voltage is equal to 237.8 volt, and the max current is equal to 237.8 milliampere. Now we will look at the power consumed by this resistor. As you can see, the average power by the resistor is equal to 21.78 watt. Now we will look at the inductor peak voltage. As you can see, the peak voltage is equal to 7.03 volt, and the peak current is equal to 237.767 milliampere. Now we will look at the power by this inductor. As you can see, the average power by this inductor is 68.711 microwatt, which is almost equal to 0. Now we will look at the peak voltage by the LED. As you can see, the max voltage is equal to 2.238 volt, and the peak current is equal to 788 milliampere. Now we will look at the real power absorbed by this LED. As you can see, the real power absorbed by this LED is equal to 302 milliwatt. So by looking at the circuit diagram, you can know that this is a three-phase system because each phase is at a different time. Now I will pass it to my teammate Kurt Ming Teng to explain about the analysis.
Thank you. Now I will discuss about the analysis. We will compare the components measurements and calculations component. First, the component is capacitor voltage. The measurement that we get is 237.9 volts and the calculation is 239.94 0 degrees volt. And the next component is capacitor currents. We get 762.5 milliamperes and the calculation is 0.754 and 90 degree A. Capacitor real power 0.0 W and the calculation is 0 W. The resistor voltage 237.8 volt measurements and 239.9 negative 1.8 degree volts is calculation. So the next one is resistor current. Resistor current we get is 237.8 milliampere measurements and 0.2399 negative 1.8 degree calculations. So the next one is resistor real power to 21.79 watt and the calculation is 28.76 watt. The inductor voltage we get is 7.031 voltage and the calculation is 7.536 and 88.2 degrees. Inductor current is 237.8 milliamperes and the measurement is 0.2399 negative 1.8 degree. The inductor real power is 434 microwatts and 0 watts from the calculation. The LED voltage is 2.238 volt and the calculation is 2.238 0 degree volt. And the LED current is 787.3 milliamperes and the calculation is 0.788 and 72.19 degree amperes. LED real power is 0.299 watts and the calculation is 0.2697 watts. Thank you.
Now I will present the part of discussion. As you can see, there is the table of percentage difference between the calculated and measured value. For the capacitor, voltage is 0.85%, while for capacitor current is negative 1.13%. The capacitor real power is 0.1% and resistor voltage and resistor current is 0.8%. The resistor real power is 24.23%. Inductor voltage is 6.7%, while for inductor current is 0.8%. Inductor real power is 0%, while for the LED current is 0.09%. Last, for the LED real power is negative 10.86%. There is some challenge that we faced while during the project. For the first is the academic schedule is very tight, so that our group is decided to design a simple 3-phase circuit. For the second challenge that we have faced is had a hard time to find the most suitable circuit for this project, as we had researched many types of circuits and they are hard to analyze for our current study level. Now for the part of future improvement, our group will try our best to research more about the 3-phase circuits and AC electrical circuit analysis so that we can produce a more professional and more content project. For the next improvement is we will communicate more with other professional workers that are related to electrical engineering so that we can gain more insights about this project.
Last, I will discuss about the conclusion. In this project, we successfully designed, simulates and analyze a balanced 3-phase RLC circuits. By combining theoretical calculations with simulations and practical measurements, we understand the fundamental electrical concepts such as phases, impedance, RMS value and many more. We had also achieved the objective. For example, we have constructed a 3-phase circuits, performs calculations and use online circuit simulations software to simulate the circuit. The analysis confirms that the theoretical predictions agree well with most measurements and simulations. Overall, the project helped us to learn more theoretical knowledge, develop our circuits analysis skills and improve our ability to interact. That's all for us. Thank you.